uppe. Jag springer och kollar hur det ser ut där borta på stånd.
Vart är de?
Vänta nu. I FL.
Men är det inte bättre att bara gå in? Eller hur?
Ja, men
Good evening, everybody, and welcome to Chalmers Formula Student Design Presentation 2021. My name is Daniela.
And my name is Simon.
And we will guide you through this evening's event. Let's begin then.
Yeah.
The agenda for tonight is as following.
Oh, first, a great thank you to all of our sponsors. And now we will show you the agenda.
Yes, there we go. And so we will begin with telling you what Formula Student is, continuing with what Chalmers Formula Student is, and talking about the design of our car, and we will end with a Q&A.
Yes. And for those of you who don't know, this is a presentation of Chalmers Formula Student new racing car concept.
Yes, and we're sure that many of you have many questions for us. So the Zoom link, you can find it in the description box below for the Q&A that will be after this presentation.
Yes. So let's get started. We first of all want to talk about what Formula Student is. And Formula Student is the largest engineering competition for students in the world. The teams design, build, test, and race with the cars. And universities all over the world travels and compete during the summers.
Yes. Moving on.
Yes, as this is not wheel-to-wheel racing, you are evaluated instead on how well you do in different events. So each event gives you a certain amount of points, and the team that scores the most points wins. Easy to understand, but hard to accomplish. The competition consists of dynamic events, and the dynamic events consist of different tests measuring the performance of the cars.
Yes, and the static events challenges the team in business, manufacturing, and design thinking. So, moving on to what Chalmers Formula Student is then. We are a course given at Chalmers University. It was founded in 2001, and since 2014, the car has an electric powertrain. Even though this is a course for first-year master students, we welcome bachelor students to contribute to our team with their knowledge and passion. But none of this would be possible without our amazing sponsors.
Yes. So, if we take a look at the project life cycle, you see that we've been through the pre-study phase where we learned about rules and what needed to build a car. And then we went through the design phase where we designed the new features for the car. And now we're in the manufacturing phase where we're actually building the car. And the team has been working hard since September on the design, and that's what we is soon about to reveal.
Yes. So, as we all know, this has been a very challenging year, trying to design a racing car with an ongoing pandemic. All the competitions last year were cancelled. That means the CFS20 car Madeline never got a chance to enter the competitions. So the main focus for CFS21 team was on improving Madeline and making her even better. And the results? Well, you'll see very soon. But first, let's meet the CFS21 team. We present here. Here's all of us, and we're 23 project engineers, 9 trainees, with 8 different nationalities.
Yes. And now, what you all have been waiting for, the Chalmers Formula Student 2021 car. We will first show you a video of the car, and afterwards, the design subgroup will tell you about the new features. So fasten your seatbelts, because here we go.
Hi! Now you've seen the new design of the CFS21 car, and we are very proud of it. Now let's dive into the subgroups, listen out on what their responsibilities are, what they have been making new, and what upgrades have been made. Let's begin with business and management. We have myself, Daniela, together with Olympia, Erik, and Simon. So our subgroup differs a bit from the rest because we don't really design anything on the car. Our role is more or less to keep the team together. So our responsibilities are internal communication within the team and the subgroups, and external communication, for example, sponsorships. We are also responsible for 2 out of the 3 static events on the competitions, which are business plan presentation and cost and manufacturing events. So what is a business plan presentation? The objective of it is that we as a team create a business model surrounding the competition car and show the judges that we can make a financial profit of it, and they also judge our delivery on it. The judges are seen as investors. And what is the cost of manufacturing event then? The judges evaluate the team's understanding of the manufacturing processes and costs. Our understanding of making a decision between buying a part and making it, the trade-off decisions basically. So to summarize business and management, we basically keep the communication flowing in the team, and our main focus is on the static events. Next up is aerodynamics with Marcus and Vicente.
Hello, my name is Marcus, and I'm one of the members in the aerodynamics subgroup. The team consists of Christian, Edwin, Daniel, Carl, and Vicente, and together we have redesigned a complete new Aero package for the 21 season. The highlights for this year is that we have added the front wing DRS, added front wheel deflectors, an integrated cooling package, which together with the changes have led to an increase in 8.3% in total downforce of the car. Next up, we're going to deep dive into each specific part of the aerodynamics. The front wing is a complete new design. And the reason for this is that we learned from last year that the front wing generated too much downforce and we're too aggressive. But now you're probably thinking, is there something as too much downforce? Isn't that the sole purpose of an aerodynamic part? And yes, you're right till a sense. But only if all of the parts work simultaneously as one unit. Therefore, the biggest challenge this year has been to create a front wing that generates as much downforce as possible without neglecting other parts. And the problem with being the front wing guy is if I maximize the front wing downforce, I would neglect the side diffuser and the floor. This due to I will feed the side diffuser and the floor with turbulent air. And turbulent air means less energy air, meaning that the side diffuser and the floor will be neglected, leading to less overall downforce. This have led to the concept that you can see in the picture, which have also led to a decrease in 12% in front wing downforce. But don't be frightened. Those 12% actually make it possible for us to increase 8% in total downforce of the car. This leads us to the next problem. Doesn't the motor with the wheels along with the front wing create turbulent air? And yes, it does. So in order to solve this problem, we have added the front wheel deflectors. This to guide away the turbulent air created by the front wing and the wheels and the motors away from the side diffuser. And now you're probably thinking as well, with all of these perks for the side diffuser and the floor, does the front wing even create any downforce? And yes, it does. Most of the downforce on the front wing is created on the outer portion of the segment. And there you also can see the flaps. And by creating most of the downforce there, we also create most of the drag. Therefore, this year we have implemented the drag reduction system, DRS, that we previously have had on the rear wing. This led to a 44% reduction of overall drag. The DRS system will be actuated on the straights, and this leads to that less energy is required to gain speed, less energy is required to maintain speed, and the possibility of running greater speed than when having the DRS closed. Next part in the aerodynamics group is the rear wing. And the rear wing is built up by a 3D segment. And for those of you that still wonders what a 3D segment is, it's explained by the ups and downs on the rear wings that you can see. So for example, the sides of the rear wing are lower than the middle. And by having the sides lower, it makes the possibility to push the rear wing harder and create more downforce. But the reason to why we don't run the middle segment as low as the side is because of the driver's head and the helmet. The helmet creates bad turbulent air, and in order to get away from this air, we have raised the middle part of the segment. Add-ons from last year is that we have put on lower flaps under the main segment. This has led to a 5% increase in rear wing downforce. And one of our prides with our rear wing is the mounting solution. Before you start thinking that, oh, shouldn't the rear wing be our pride? It is our pride, but we're also very proud to have done a great mounting solution. And the reason for that is because it's very light and it sits snug between the rear wing and behind the driver on the roll hoop. And because of this position, the mounting solution in itself does not create more turbulent air than the roll hoop in itself does. And that's, from an aerodynamic perspective, is what we're striving for. And next in line is the side diffuser, who Vincente is going to talk about.
Hello, my name is Vicente and I'm going to present the side diffusers and the rear diffuser. So the side diffusers, they use the air deflected from the front wing and the underbody of the car to generate downforce. They have been completely redesigned for this year. There has been a 25% increase in downforce, and that's mainly due to an optimized main duct with a carefully designed shape that has an increased expansion ratio and is also easier to manufacture. There are inlets in the front of the part that induce high energy vortices into the main duct that aid with keeping the flow attached to it, increasing downforce. Also, the back of the part has an open design which allows more airflow towards the rear diffuser. And now for the rear diffuser, to maximize the underbody pumping, the volume for pressure recovery has to be maximized. This required an aggressive diffuser angle, which is basically impossible to obtain while keeping the flow attached. By integrating the cooling package into the rear diffuser, a suction normal to the flow is introduced to the duct. This helps with keeping the flow attached and also increases the extraction of air. The diffuser is fed by high energy air that bypasses the side diffuser, which improves mass flow and generates powerful vortices together with the strakes. And now I'm going to pass it on to Frame with Wilhelm.
Hello, my name is Wilhelm and I will be representing the frame subsystem. My teammates are Arda, Achilles and myself. We are responsible for, among other things, the monocoque and the driver ergonomics, and are therefore the main interactive system between all the other subgroups. One of the main roles is to incorporate the safety requirements without compromising much on the race performance. It is a single-piece carbon fiber monocoque with aluminium honeycomb core, and with all its attachments weighs about 19 kilograms. The restraining harness is a 6-point system, ensuring complete safety. My contribution, and the biggest focus this year, is through the ergonomic driver optimization, where I collaborate with the drivers for their input into the different subsystems with regards to cost, time, rules, and manufacturing. We have in CFS developed a rigid system to design for the drivers, as they are in the end what makes the car to perform. Meanwhile, we continuously develop the process for future generations. What's newly designed for this year is the head restraint, the steering wheel, and improved driver support. The steering wheel was designed iteratively with regards to the driver's requests of layout design, grip, graphical user interface, and dimensions, with several prototypes before the final design. This created a very clear template of what was required for an optimal driving experience, and it was made accordingly. The general grip shape is modeled over a clay 3D scan that was fitted to the driver's hands, which created a better palm support and thumb support, especially required for the endurance racing. The controls are positioned to be within a certain thumb radius, ensuring comfortable interactions on track, as well as paddles for region and torque vectoring control. For the graphical user interface, a usability test was performed on the drivers to help the low voltage subsystem to design the color scheme and properties for racing situations. This is to convey information effectively without being a cognitive burden on the driver. The steering wheel is finally dressed in a friction material. Stress tests show an improved lower deformation in an impact situation than the previous design without being heavier. The head restraint was designed to be a self-supporting structure, which is a bit different from the previous years, where it has been attached to the main group structure, mainly to ensure rule compliance and open up the design space for more variations and multifunctional interactions between the subsystem. The final design shows an improved overall downforce, helping the rear wing by 3 newtons, which was achieved through several iterations. But due to its volume increase, space efficiency had to be regarded because of the close approximation to the other systems. During the development phase, several aspects to improve lateral force support to the drivers was regarded and implemented in the padding. Finally, the general mass reductions is calculated to be about 15% due to an efficiency in metal inserts and core material. And now I will hand over to Adil, who will talk more about the suspension.
Hello, my name is Adil, and I'm a member of the suspension subgroup. And we are responsible for the vehicle dynamics of the car, and the actuation system, the linkages, steering, and the tires, all to turn power into traction. So who have I been working with on these things? Well, we have Robin, William, Fredrik, Sia, and Jasson. Some of the subsystems in suspension was inherited from CFS20, like the hard points, the pedal box, and the brakes. So what I'm going to do is touch upon some of the improvements. The first thing I want to talk about is the actuation system. The actuation system that we have on the car is called the Aero system, and it decouples the heaving roll motion of the car into its own spring and damper. This allows for independent adjustability for the spring and damper coefficient for the two motions instead of having to compromise on them. The focus for improvements for this year was to ease manufacturing and assembly while reducing compliance and still being weight effective. So let's dive into a little bit more detail. First, we have the compression structure. The main goal of the compression structure was to ease manufacturing. The structure is more stable with the new fork design compared to the previous roll design. There are fewer parts overall in the assembly, not a single screw in it. And this makes it lighter by 39%. And the simplicity of this will make it easier and faster to change the spring and adjust the damper on the move during testing so you can get the best performance. And to get the most out of the suspension, you want as much load going into the springs and dampers as possible, which requires a system that is robust. The carriers is the connection between the actuation system and the monocoque, and therefore they must be robust. Compared to the CFS20 carriers, the new one has an interconnecting rod between the left and right carrier. This bar was added because of a different simulation setup that takes the flex of the monocoque into account instead of assuming a stiff mounting. The simulation considers different driving conditions, such as left turn, right turn, braking, and so on. And all of this resulted in an increased stiffness from 46 to 70% depending on the condition. And the deformation went from 1 mm to 0.3 mm. And the new design also makes assembly easier, since the bar connects the two carriers having alignment issues minimized. But this bar of course makes the carriers heavier, but with an up to 70% increase in stiffness, the 38% weight penalty is well worth it. And just like the actuation system, we want to minimize compliance throughout the whole suspension, but we still want to be weight effective, and to be able to do this, we have been working with some of our partners to 3D print components. And the benefit of going with 3D printing is the freedom and complexity you can have in design, and at the same time reduce manufacturing effort. And all of the parts will be 3D printed or topology optimized. First, we have the rotating bars, which are very visually pleasing parts, and they are part of the actuation system and connects the compression structure with the carrier to transfer the load from the wheel and push rod to spring and damper. And the rotating bars will be printed by EOS and titanium. Then we have the triangles. They connect to carbon fiber tubes to form the linkages. They will be printed by RISE in aluminum. Finally, we have the uprights. The uprights will also be printed by EOS and they will be in aluminum. The upright is the interconnecting part between the electric motor, the gearbox, the brakes and hard points. And the main goal of the upright was to maintain the stiffness and reduce the weight. And the weight reduction on the uprights is 72% for both the front and rear. As you can see, 3D printing enables geometries that otherwise would not be possible, like the skeleton design of the rotating bars, with the rear upright looking like the Swedish moose, where it has gotten its in-house name for, the moose design. And the upright is the part of the wheel assembly package, but there has been quite some exciting changes. So now I will hand over to Achilles and the wheel assembly group so they can explain more.
I'm pretty sure you've heard the saying, don't try reinventing the wheel. Well, this year we really didn't get the memo. The wheel assembly subgroup is responsible for packaging the gearbox, brakes, uprights and electric motor into the wheel. Hi, I'm Akhilesh, part of Frame, and along with me I present to you members of suspension and mechanical powertrain who are responsible in this subgroup. The rims. Since we are running 18-inch Hoosier RB25 tires, we use the tire data provided by them to develop a single-piece carbon fiber reinforced polymer rim. This rim has a diameter of 10 inches and it is 7 inches wide. A particular problem that we faced this year was to ensure that the rim offset is set to 17 millimeters. Now you'll be wondering what the rim offset is. It's the distance between the contact surface for the hub to the center line of the wheel. By having a 17 millimeter rim offset, we were able to move the entire wheel assembly into the rim. Thereby, the aerodynamic drag experience while the car is on the track is reduced. An enlarged hub contact surface ensures that there's more load transfer happening towards the chassis, and while optimizing the design for the rim, we have a 10% decrease in weight. Our focal point while doing this was to ensure that the stiffness of the rim is maintained so that the deflection of the camber and the toe angles especially is kept as minimum as possible. Now on the big picture, the wheel assembly subgroup has managed to achieve the following statistics. There's a weight reduction of 19% and there's 5% decrease in rotational mass. The outboard motors have been moved into the rim by 76 millimeters, and the steering bracket, which is mounted onto the uprights, has an adjustability range of 25% anti-Ackerman to 35% anti-Ackerman. This gives us more adjustability during testing and to find the right suspension setup to help us go faster on the track. Now I will hand over to Anton, who's going to be telling you about the gearbox and the mechanical powertrain.
Hey, I'm Anton from Mechanical Powertrain, and I have designed this year's gearbox. The gearbox is attached to the uprights and the motor, as well as the brake system, and it's also the mounting point for the wheel, so it's a very centralized part in the wheel assembly. It has a gear range of 1 to 13, where it transforms the power from the motor of 24 Newton meters and delivers a total power output to the wheel of 330 Newton meters per wheel. And the car has 4 wheels, so it gives a total of 1200 Newton meters for the full car. A car that weighs 200 kilos. So if you take a look inside the gearbox, down here, looks nice, if I may say. Well, the change this year is the rotating parts in the gearbox. To the right we see the planet carrier, which earlier year has been acting as the hub for the wheel. So it means it's a rotating part. And the plant carrier is also the heaviest component in the system here. So when that starts spinning, it generates a lot of rotating mass. And that's something we're trying to avoid. So by decreasing this, we developed a new component, the gearbox housing, we see to the left. And it works, it transfers the power with the help of the ring gear you see in the middle, making the gearbox housing spin, rotate, and transferring the power output to the wheel, making the car go fast. Very, very fast. Here we see the mechanical powertrain system. It contains of the motors and the gearbox, also the cooling system and other power output components. The team is me and Joel for the cooling system and Mohammed for enclosures and containers. What we want to improve this year is, as I mentioned, the gearbox concept, as well as improving the cooling system with new radiator placement and fans, and also modifying the rear duct. But that will Joel talk about, so I'll leave it to him. So thank you.
Hi everybody, my name is Joel and I'm responsible for the cooling of this year's car. If we take a look at the radiator and fan assembly for this year, we've moved the position of them from behind the rear wheels to the diffuser and integrated it. And as Aerodynamics pointed out before, the purpose of this was basically to increase the overall downforce of the car and also to reduce the drag as we have less surface area. For the mechanical parts of this subsystem, we clamp the radiators with a carbon fiber duct, and then we also have a carbon fiber mounting connected to the rear hatch to support the whole assembly. Moving on to the rear ducts, basically the focus areas of this part has been to exhaust the hot air coming from the battery to prevent it from overheating. We've also wanted to maximize the space behind the rear hatch so that the new radiator and fan placement is possible. And then lastly, we also want to redirect the hot air coming out to not hit the radiators, as this will lessen the cooling power of the car. Now I'm going to hand it over to Saraswati and the electronics subgroup.
Hi, I'm Saraswati and I'm a member of the electronics subgroup. We work on the electrical powertrain, the low voltage system and the software used in the car. My teammates are Anna, Isak, Supun, Robert, Matteo, Axel, Nils, Sebastian and Lakshmi. Alexander, Henrik, Mats and Albin are the electronics trainees. So let us start with an overview of the electrical system. To start with the high voltage system, we have the battery. This is what stores the energy that is used to run the car. Our battery is designed to have a maximum voltage of 580 volts and stores 6.5 kilowatt hours of energy. The relay box has printed circuit boards which monitor and control the battery. It also has the DC to DC converter which steps down the high voltage of the battery to 24 volts so that it can be used by the low voltage system. The power electronics box houses the inverter which converts the DC power from the battery to AC power. This power is then carried through the tractive system cables or the high voltage wiring to the motors. The running of the motors is what makes the car move. Since our car is an all wheels driven vehicle, each of the motors is controlled independently. In this image, we also see a few parts of the low voltage system, such as the steering wheel and the rear and front nodes. These nodes collect sensor data from across the car, and using their software safeguards, they enhance the safety of the car. So this year, since we have quite a few carryovers from CFS2020, we are going to highlight mainly the new features of our design. This year, a new graphical user interface has been designed for the steering wheel. And here in this slide, we can see a few mock-ups of the same. This interface has different modes, such as a stationary mode, which is the default mode when the car is in standstill, or a racing mode, which can be entered by selecting the dynamic event, as shown in the first figure. It also has different indicators, such as an indicator of error when something is not how it should be. It also indicates when the drag reduction system or the regenerative braking is on. In the second and third figures, we see two different scenarios during the endurance event, the longest dynamic event. In the first case, the car has been pushed too hard too soon within the first 9 kilometers itself. The energy of the battery has been depleted, and with only 2 kilometers worth of energy left, the driver is not going to be able to finish the endurance event. Ideally, we would like to keep the efficiency goal above the white line. In the second scenario, we see that the driver has managed to balance the speed of the car and the energy of the battery really well. This driver is going to successfully finish the endurance event. Thus, the new graphical user interface can be a useful tool for the driver to make better decisions during the dynamic events. Now, Nils will talk about the other new features of our design.
Hi, my name is Nils. I'll talk about the new inverter and the driver assist system. So this year we are developing our own inverter, and the purpose of the inverter is to control the current flowing through the motor to generate torque in the most efficient way as possible. The focus of the design has been to lower the weight and volume, and since the inverter box is currently the widest component in the monocoque, by making an inverter with lower footprints, we can make the inverter box more narrow and make the whole monocoque more narrow. The new inverter will weigh around 0.6 kilos, which is more than a 5 times decrease compared to the previous inverter. We also aim to achieve a power density of 66,000 watts, which is more than a 10 times increase compared to the previous inverter. These huge gains in performance is thanks to a new technology called silicon carbide based power MOSFETs. These allow us to achieve a higher efficiency and increase the switching frequency. By increasing the switching frequency, we can have less capacitors, and by having a higher efficiency, we don't need as much cooling, and we can make the whole design a more compact design. Even though we made the inverter smaller and lighter, we have been able to integrate more functionality into the inverter, for example the discharge circuit. And by integrating more functionality into the inverter, we can have a smaller part count and overall volume. And we plan to take this project even further in coming years. We have a road to achieve a power density of 80,000 watts per liter. We have also introduced a new advanced driver assist system. The system consists of 3 main capabilities: torque vectoring, traction control, and regenerative braking. Torque vectoring means controlling the torque of each wheel individually for optimal handling and traction. This is especially important when making tight corners, and it will lead to reduced corner times. Traction control means optimizing the torque for optimal power transfer to the ground, and this is especially important, for example, during acceleration, and it's also good for efficiency. We've also introduced regenerative braking, so the power that has previously been lost in the brakes can be put back into the battery to extend the range. And thus we can use a smaller battery, and the vehicle will be lighter and smaller. The driver assist system consists of 2 blocks. The first block calculates the actual vehicle motion and the requested target motion from the driver. And it does this with all the sensor and driver's input data we have in the vehicle. The second block, the control block, then calculates the optimal torque distribution for the 4 wheels. Next up is Joel, and he will talk more about the powertrain.
Hi guys, I'm going to talk a bit about the electronic powertrain also for this year. So for this year we have a new high voltage disconnect enclosure, a new data logger enclosure, and also the new power electronics assembly. So if we begin with the most complex part, the power electronics assembly, me and Mohammed from the mechanical powertrain has been working on the packaging of this and also the design. We can go through the different parts, starting with the power electronics stop cover. We also have the inverters, which Nils talked about before, the 3-phase connectors which connect the inverters to each of the motors, the cooling plate, which is designed to cool the inverters. We also have a power electronics mounting bracket, and this basically mounts the whole assembly to the car. We have the power electronics bottom cover to also shield the electronics, and then the data logger enclosure, which basically houses the data logger that we use on competitions. So moving on to the cooling plate, the main goal for this year was to reduce the width, weight, and also to design it for manufacturing. Basically, it's been a very iterative design process as we have a lot of different dependencies on different subgroups, especially the inverter project. For the biggest challenge, it was easily to just fit all the parts on the new cooling plate as it acts as the mount for the inverters. For manufacturing at least, we will use a 3-axis mill and we will manufacture it in aluminium. And then for the final targets, we got a width reduction of 43% and a mass reduction of 17%. Moving on to different electronic enclosures, which has been designed by Mohammed from the mechanical powertrain. Basically, the power electronics enclosure will be designed by carbon fiber for low weight and electric safety. We have managed to decrease the width by 43% and the height by 32%. Unfortunately, this led to a 5% length increase, which made the packaging tricky, but we will get to that later. For the data logger enclosure, this will be 3D printed in PETG, a plastic. And basically the challenge about this part was just to make the mounting possible on the power electronics enclosure, as we have a lot of parts, as I said before. The final part for the electronic enclosures is the high voltage disconnect enclosure. This will also be 3D printed in plastic, and basically this houses all the electronics for the shutdown circuit of the car. So, and here we go to the last one. This is the packaging of the rear of the car basically. And as you can see, it's pretty tight. So with the power electronics enclosure, as we had a 5% length increase, this meant that we kind of had to redesign the data logger enclosure and the high voltage disconnect enclosure just to get everything to fit. But yeah, we managed to do it and we're really happy with the results. Thank you.
Du kan se den första.
Ja, jag ser goosebumps, right? Exciting, right? Now, a small look on what we have ahead.
Yes, as I mentioned earlier, we're now in manufacturing phase, and our target is to complete the car, test it, and if the pandemic allows it, compete in Formula Student competitions. And we once again want to thank our fantastic sponsors helping us out, because without you we are nothing.
Yes, and also we need to send out an extra big thank you to our CFS manager Anthony Kaltrich for the amazing release video of the design, and as well our CFS friend Jakob Brillante, who helped a lot with this live. So we're coming to an end on this broadcast, and now it is time for the Q&A. I would like to remind you once again that the link is in the description box below, and you will meet all of the team members and ask them all your burning questions. When it's time for our launch event in the summer, we hopefully can do it physically and meet you again. But until then, take care and have a good night.